So let's talk about logistic regression. Logistic regression, like linear regression, is a linear model that associates multiple predictor variables and controls for each of them and their association with a single outcome variable. There are different types of logistic regression, but generally, when we say logistic regression, it refers to a model where the outcome variable is binary. So yes or no, disease or no disease, etc. Any binary variable, which we of course often translate into a zero, one or zero in the actual value of the column. Now, logistic regression in machine learning terms is a classification model and not a regression model. But this is confusing because the distinction between classification versus regression is new, and so-called logistic regression is an older term. So maybe they would change it to logistic classification, but I would not recommend you to wait for it. So the logistic regression model looks very similar to a ordinary least square linear model, which we have examined before. And the main difference is that the outcome variable, once again, is binary, and it's structured in logarithm and odds in odds terms. So ln is the natural logarithm of the probability divided by 1 minus the probability. So that is, as we mentioned before, the number of the ratio of the probability of something happening divided by the probability of it not happening, right? So P for probability, and that's the main difference. So if we have an example, for example, diabetes, we may have diabetes as the outcome variable, and then we may have multiple predictor variables, and the predictor variables may be continuous or categorical or binary. So things like age, blood sugar, weight, maybe gender, and we can conceive of the model in this general way, but when you actually load the data into the logistic regression, I just wanted to emphasize here that it will turn it into a logarithmic base, okay? And then we're going to have to sort of reinterpret the coefficient, but it's not that difficult if you just take the steps one at a time. Let's remember also some assumptions of logistic regression that most of which are the same for linear regression, and they apply to it. So one is that the relationship between the predictor and the outcome variable is linear. So if you don't have that linear relationship, which you can see by just graphing the relationship, you should not employ logistic regression. But note that the linear relationship is that should be between the predictor variable and the log odds of the outcome variable. So if you actually want to see in a graph like a line graph or a scatter plot, if the relationship is actually linear, you have to use the log odds of the outcome variable as we saw over here, not just the 1 or 0, because if you just use 1 or 0, then you're just going to have two categories. You're not going to be able to visualize the linear relationship. Second point, you can create a simple logistic regression model with a single predictor, or a multiple logistic regression model with multiple predictors, as we also saw with the linear regression. We only have one single outcome variable, so also this is the same, but we can have multiple predictor variables. And the predictor variables should not be correlated with each other. That is, we should not have multicollinearity. Maybe we didn't talk much about this before, but that's one of the assumptions of the logistic regression model, just like the OLS, regular simple or multiple regression. Also, once again, in Logit, you have to make sure the outcome variable is indeed binary. If it's not, you need to use a different model. And that's a little something about logistic regression. Next, we're going to be talking about applying it in Python.